Okay, hello everyone. This video will show you another example for drawing the shear moment diagram. Yeah, and this is getting more and more complicated. Okay, okay. So, just like we did before you draw the shear moment diagram, you need to calculate using the rigid body equilibrium to calculate the reaction force or reaction moment from the support. Okay. And so let's see, here is a beam and subject to the external loading here, 8 kilonewton point down, and this is distributing loading here, 50 kilonewton per meter point down. And also there's external moment, 20 kilonewton meter and clockwise. Okay, clockwise. And here is a support. A is a pin support. B is a roller support. Just the same setup we used, same setup before. Okay, so first of all, let us draw the free. Maybe I would say I would write. Okay, A, just make point again. A is a pin support, and B is a roller support. Okay, and then we draw the free body diagram of this beam. Okay, so let's say it's look like this. The rod look like this. And the point A, because the pin supports, so it has reaction force on x direction and y direction. So, and this is a y, this is a x. And okay, and it say here we have the 20 kilonewton times meter as its clockwise moment, 20 kilonewton point m. And also here is a force point down. Okay, it's a kilonewton, and here is the okay. Here is another. So there is a distributing load here. Okay, 50 kilonewton per meter. Okay, and here is B C. Oh, sorry. C. I think R. Sorry, B is here. Okay, B is here. And it give us some geometry information. Okay, let's say what's the geometry information. He said the last, okay, here the last part is 3 meter, and this part is 2 meter, and this part is 1 meter, and this part is 2 meter. Okay. Okay, that's just the free body diagram of this beam. Okay. And we have to keep using the rigid body equilibrium to calculate the reaction force of, sorry. There is a reaction force here. It looks like it's hard to draw. There's a reaction force at B. Okay, here is the B. Okay, B, Y. Okay, here's a reaction because B is a roller support. There's a reaction force from B. Okay. Okay, okay, we have to solve the AY before draw free body diagram, shear moment diagram. We have to solve the AX, AY, and BY. Okay, and then we have to use a rigid body equilibrium. Okay, and then you're using the rigid body equilibrium, and we see here is we have the distributing loaded. Okay, so when we want to do the rigid body equilibrium, we have to do the simplification of this distributing loaded. Okay, distributing loading has two goals. One is find the magnitude of resultant force and the position of resultant force. And the magnitude of resultant force is area under the distributed load curve. Okay, so the magnitude is okay. The height is 15 kilonewton per meter, and the width length is 3 meter. So the magnitude of resultant force is 45 point down. Okay, so we have to erase this. Okay, it's 45 point down. It's 45 point down. And what's the position of resultant force is right at the centroid. Okay, so here I think here is a centroid of this distributing loaded. Okay, the central distributed load is I think is about here. So I think here is I believe here is 1.5. Okay, so let's say here is 1.5 meter. Okay, okay, so let's we do the first one. Well, we do a simplification of the distributed load. Okay, and next we use the rigid body equilibrium to calculate x, ay, and by. Okay, so summation fx equal to 0. Let's say, okay, the horizontal force we only have nx equal to 0 and x must 0, so nothing we can do. Okay, so and vertical force, let's see, we have ay point up, and this is a moment. Yeah, just ignore it. And we have the a kilonewton. This is not force. Okay, this is a moment. And the force here is a kilonewton point down. Okay, so it's minus a, and we use kilonewton as a unit. Okay, ay, and this 4 a kilonewton point down, and we have by point up. Okay, and we have this resultant force here, 45 kilonewton point down. Okay, and then add together is 0. So we have this equation, ay plus by is 53. Okay, and the unit is kilonewton. Let's make a note here. 53, yeah, yes. Okay, and then with the whole system, the total moment of the system is also equal to 0, and you choose A as reference point. So we don't have to consider X and Y, okay, because these two forces won't create a moment with respect to A. So here we have the 20 kilonewton times meter, and it's clockwise, so we have minus 20. And here is a kilonewton point down, and the lever arm is here. Yeah, be careful to calculate lever arm. What's the distance here? Distance here is 1. It is 1, and here's 2, so lever arm is 3, and point A point is here, and it's clockwise rotation. So it will minus A times 3. Okay. Okay, so and also here, this force will also create the counterclockwise moment, counterclockwise rotation moment. So here's a by, so it's counterclockwise, so positive, and the by, and what's the lever arm here? Lever arm, because here's 2, here's 1, here's 2, so it's 5. And the final one, this resultant force will also create a moment with respect to A, and it's clockwise, so it's negative, and its magnitude is 45. And what's the lever arm? Yeah, here is 1.5, be careful, here's 1.5, and the 2, 1, 2. So it will become totally 6.5, right? 6.5, yeah, 6.5. And then, and together it becomes 0. Okay, let's see. Do I have the right equation? Let me check my notes. Yeah, it's correct. And okay, and then use this equation, you will see you can solve the by directly. Okay, so by is equal to 67.3, and it's kilonewton. And you have by, and then you have ay. Okay, of course you can get ay, and ay is become negative 40.3 kilonewton. Okay. Oh, is this correct? Oh, maybe I make some. Let me see. I think it's not right. Minus 67.3. Oh, minus 40.3. Okay, minus 40. Yeah, okay. So you see the ay is negative. That means it's point downward. Okay, so we have ay, by, and x. Yeah, okay. So right now we can draw the shear moment diagram. So we first of all we draw the shear diagram first. So shear diagram. Okay, let me see. Let's say. It's difficult here. Okay, so let's draw this. Yeah. Very hard to draw a straight line. So it's a shear force, and we use kilonewton as a unit. And about, okay, x is here. Okay, we draw from A. Okay, we draw from A. So let's start with A. What's the shear force at A? External shear force, and we keep it stress line. This is external shear force. Okay, external shear force. Okay, so AY is minus 14.3. So This will is starting point minus, let's say maybe here I call it minus 14.3 kilonewton. Okay, and during the from this position to this position, from 0 to 2, from 0 to 2. Okay, I say here from 0 to 2, there is no external force. Okay, external force. So mine is so the there's no external force, so the shear force will keep the same value. So it's in the to the point 2. Okay, and here at this position 2, there is only external moment. There is also no external force. So it still keep the same value. So it still keep the same value, right? Okay, so it keep the same value. Okay, at the position 3 here, it experienced a kilonewton point down. A kilonewton point down. So right now we at the minus 14.3. Okay, so minus 14.3 and the minus a kilonewton was the value be minus 22.3. So this will go down to okay here. Go down to here. Okay, maybe I draw here it's minus 22.3 here. Okay, so then and between 3 and the 5 there is also no external force, so the value, so it'll keep the same value here. So and here's 3 to 5. Okay, it's 3 to 5. 3 to 5. And at this point B, okay, be careful here. At this point B, we have a reaction force point up here. B, we have reaction force point up. And what's the value? 67.3. So right now we have minus 22.3 and minus 22.3 plus 67.3. What's the value? What's the value? Okay, I think it's easy, right? So I think it's 45, right? 45. So that tell you 45. So let's say at this position, we have the reaction force from the roller support, and it's plus 67.3, and it will become 45. Okay, 45 is here. Maybe I need to write here, put here. 45, let's say if we draw in scale, 45 might be here. Okay, it's 45. Okay, so it's 45. Okay, maybe I should draw more straight. Yeah, more straight, more straight, more straight. Okay, 1.5. Okay, and at this position 5 here, and then it's subject to the distributing loaded point down, distributed point down, and it's 50 kilonewton per meter. Okay, so here is with 45, and there is 50 kilonewton per meter, and its length is 3. So we have 45 right now at position 5 with 45, and we have 15 kilonewton point down, and its length here distributed the load, the length of distributed load is 3. So you add this together, you find it will goes to 0. Okay, so between these 5, so 5 to 8, maybe I just draw 8 here. So the 5 to 8, it will finally become, it's back to 0. Okay, up, yeah, here, back to 0, back to 0. Okay, and then back to 0, it's straight line. It's steadily decrease. It's steady. It's steady decrease, or is this decrease? Yeah, keep ask the same question. Is this decrease or this decrease? Okay, which kind of decrease? Because this is uniform distributed load. Okay, if you slice the area of distributed load with dx, with the width dx, you see the height is the same. That means the area of each slice is the same. So the change of the shear equal to the area under the distributed load. The change of the shear equal to the area under the distributing load. So each tiny area is the same. Each tiny area is the same. That means the change is the same. The change is the same. So it's steady decrease. So this will be the final shear diagram. So this will be final shear diagram will be like this. Okay, so this is a shear diagram. Okay, and the next is the moment diagram. Okay, and then be careful. And then once again, you see the shear diagram, you finally back to zero. That means we are drawing the right. We are drawing the right shear diagram. Okay, it must be back to zero. Okay, okay. The next one is the moment diagram. So the moment we use the I think we use kilonewton times meter. I think that's we going to use. And now let's see. I think maybe draw in this way is better. Draw this way is better. Or X. Okay, so we still start from A. At A there is no moment, so this is zero. So we start from zero. And okay, and then we see the change, and then we follow the same concept. The change of the moment equal to the area under the curve. Change it over equal to the area under the shear diagram curve. Okay, so we see from 0 to 3. Maybe we can draw the direct long. Sorry, the change the moment between 0 to 3 equal to the area under the shear diagram. Ah, ah, okay, so what's the area for area what's the area for the area one? Okay, so here is a minus 14.3. Okay, maybe I erase the calculation here. Okay, so maybe I will also clean up this rich body diagram calculation, rich body equilibrium calculation. Yeah, maybe we don't need this anymore. Okay, we need more space to do the calculation for the moment diagram. Okay, and yeah, let me move my here. Okay, the final one is a moment diagram. Change of all moment equal to the area under the shear diagram. Okay, the area one. So, sorry. So, what's the area? Very easy, right? Minus 14.3 and times 3. So what's the value here? Mm, mhm. Sorry, I cannot draw to 1 to 3 directly. We have to draw to 2 first. Okay. Sorry. Okay, be careful. It's very easy to get it wrong. From moment diagram. We have to draw 0 to 2 first. Okay, because at the position 2, there is the external moment here. So we cannot draw the 0 to 3 directly. So we have to draw the 0 to 2 first. Okay, so 0 to 2. So maybe, okay, maybe I need more cut here. Okay, so, okay, the area 1, yeah, the area 1, what's the area? So minus 14.3 and times 2. So what's the value? Is minus 28.6. Okay, so let's maybe here, we draw here. So minus 28.6. Okay, it's here. And okay, and the decrease is steady decrease or increase with the increasing rate, or increase but with decrease rate. Because this area is rectangular, so rectangular slice the tiny area rectangular. With dx, the height is the same. That means the change is steady, the same. I mentioned this in the previous video, so I don't want to address it in detail. So this will be steady decrease. Okay. So and at the position 2, there's a external clockwise rotation. Okay, at 2, okay, at 2 we have the external minus 20 kilonewton moment. Okay. So, and I keep saying that the moment diagram is actually the internal moment diagram. It's internal moment diagram. It's internal moment diagram. So, so right now we have the external moment at the position 2 and it's minus 20 kilonewton times a meter. That means the internal moment at this position is plus positive 20 kilonewton times per meter. So we have to minus 28.6 at 20. So it will be minus, it will become minus 8.6. So maybe I'll draw it here. I'll draw it here. So here is minus 8.6. Okay. So, okay. So, okay, maybe here. Okay. And from the position 2 to position 3, there is no external. Oh, sorry. From the position 2 and sorry. From the position 2 to position 3, yeah, we see the shear diagram. Yeah, this has an area here. Uh, here's a state. Is area here. So here's an area here. Okay, 2. So what's the area of an area 2? Okay, area of area 2 is minus 14.3 times. This is 1. So it's minus 14.3. Yeah, so at position 2, the change of the moment is from the change of the moment equal to area under the curve, area under the shear curve. Shear diagram. So here we have here. Okay, at position 2, we are right now at 8 minus 8.6, and now we have to add this value to the position 3. So it's minus 8.6 and add this value, so it's minus 14.3. So it will become minus 22.9. So this will be here, very close here. So here, so I say it's minus 22.9, and this is rectangular, so it's a steady decrease because negative, so it's steady decrease. So here is the second part. Okay, here's second part here. Okay, and after the position 3, okay, after position, yeah, be careful, you share diagram. Oh, between the position 3 and position 5 here, position 3 and position 5. Okay, what's the area here? What's the area here? Well, the area here, okay. Okay, the area here, area 3, what's the area for area 3 is, be careful, here is minus 22.3. Minus 22.3, and the width here is 2, so it's minus 44.6. So at position 3, we already, the value is minus 22.9. We have to add this value to the position 5. So minus 22.9 minus 44.6, what's the value? It will be minus, let me check, minus 67.5. So position by maybe a drawing scale. So here is minus 67.5, and it's rectangular, so the decrease is steady decrease, steady decrease. Okay. And the final part is from position 5 to position 8. Position 5 to position 8. And, okay, let's see. Position 5 to position 8. Let's see. I think I draw it wrong here. I think my notes is wrong. Yeah, my notes is wrong. Well, anyway, I know the right answer. Okay, here the final part is here. So, okay, the final part is here. What's the area for this area? area for? Okay, because we know we want to change the moment equal to area under the shear curve. So here is 3. Okay, let's draw it. calculate area for area 4. Okay, here is 45. 45, right? 45. 45 and the height oh no, it is the base 45. It is another base 8 minus 5 is equal to 3, and it's triangle, right triangle, and you have to divide it by 2. So what's the value here? Yeah, it's exactly equal to 67.5. Yeah, exactly. Okay, so if yeah, sorry, I didn't draw long enough. Maybe just make a little extension. Or maybe it's not still not enough. Okay, so I say if 8 is here. Okay, so we have right now at position 5, we have we're minus 67.5. We have to add this value 67.5. So you will see it's back to the 0 again. Okay, back to 0 again. Back to 0 again. So that means we are drawing the right moment diagram because it's shear or moment, you must see back to 0. Okay, and the next question, what is the change? Is it a steady change or change with the different rate? So you see this, the right triangle. I think we mentioned this before. If you see this the right triangle, if you slice is with dx, 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 the height is the same, or dx. You see the height decrease. The height is getting decreased. That means the area is getting decreased. The height decrease, the area is decreased. Okay, the area decrease. That means the change decrease. That means the change decrease. Change, change decrease. So it's steadily increase, but the rate is decreasing. So it will become like this. It's increasing, but the rate is decreasing. But the rate's decreasing, so it will become like this. So initially it will become high, but after a certain point it will decrease like this. So it will like this. Okay. So it will like look like this. And here the rate is a change. Rate is decreasing. Here the rate is decreasing. Yeah, because the rate is decreasing. So here initially is fast and the rate is gradually decreasing. So that's the curve. It's not a straight line. Be careful, it's not a straight line. So maybe I'll draw it more. I draw it more using exact rate. So up. Sorry. Maybe. Uh, so my no. Yeah, looks like I think the space is 8 to 3 is 2. So yeah. Yeah, so here's the final diagram. Okay, so I think I make some mistake on my notes, but it's all right. This is the correct answer. Okay, here the shear moment diagrams. Okay, so yeah, you need to do more practice on this. Okay, I won't say it's difficult, but just need to practice. Okay, just stop video here and see you in another video. Okay, bye bye.